Welcome all to the online lecture series on applied electromagnetic theory. In this lecture, I will be dealing with the topics from first module. Myself, Rinchu Mariam Raleigh, Assistant Professor, Department of AC, Rajagiri School of Engineering and Technology. This lecture will introduce about charge distributions, electric flux density, GAUSS'S law and its applications. And in order to understand this lecture, we need the basics of vector calculus, electric field intensity, divergence theorem. If you haven't brushed up these topics, it's time for you to go back and refresh it. When we learned about Coulomb's law, I mentioned about a point charge. But the time has come to introduce, it's not always point charge, it is also possible to have continuous charge distributions along a line, on a surface, and in a volume. And the standard notations to denote them, that is, line charge density is notated by Royal, where line charge density represents the charge per unit length and it has a unit coulombs per meter. Surface charge density represents the charge per unit area. It has a unit coulombs per meter square represented by rho s. And volume charge density is represented by rho v, and that is the charge per unit volume. It's measured in coulombs per meter cube. So suppose we have this line charge density, surface charge density and volume charge density in our hand. How will we compute the total charge? So what is Royal? That is line charge density, charge per unit length. Then how will you compute the total charge Q? Is equal to integral over L, that is the total length, integrating over the total length, Royal dl. And how will you compute the total charge in a surface area? That is Q is equal to integrating over the entire surface, rho s ds. What is it? Total charge due to total charge in a volume, that is Q is equal to integral over V rho V dV. In the previous lecture I mentioned electrostatic study about two fundamental laws, Coulomb's law and Gauss's law. And now we already learned about Coulomb's law. And Coulomb's law is applicable to find electric field intensity due to any charge configuration. Whereas in today's lecture we focus on Gauss's law. And where we apply this Gauss's law is also used to find electric field intensity. And it is very easy to apply Gauss's law when the charge distribution is symmetrical. Electric flux density. Electric flux density is represented by the letter D. In short, it is electric flux per unit area. And electric flux density, it is measured in coulombs per meter square. The electric flux due to an electric field can be calculated by psi is equal to integral E dot ds, where psi is the electric flux and E represents the electric field intensity. The electric field intensity is dependent on the medium. I hope it is clear from the expression for electric field intensity. E is equal to 1 by 4 pi epsilon 0 q by r square. So there we have the term epsilon 0. So from that it is very clear electric field intensity is dependent on the medium. The electric flux density is related to the electric field by the expression D is equal to epsilon 0 E. And electric flux density is independent of the medium. It is independent of the medium. How come it is independent? Here we have the epsilon 0 and remember the equation for E, 1 by 4 pi epsilon 0. So that will get cancelled, and on that basis we can say electric flux density is independent of the medium. Electric flux in terms of D is given by psi is equal to surface integral d dot ds. One line of electric flux, it starts from a positive 1 coulomb and it terminates on minus 1 coulomb. And electric flux density has got another name, that is electric displacement. The expression for electric field intensity obtained from Coulomb's law should be multiplied by epsilon 0 for obtaining the electric flux density. That I hope that is clear from this particular equation. We know D is equal to epsilon 0 E. So using Coulomb's law, we can compute the electric field intensity. Multiplying that by epsilon 0 will result in electric flux density. In the previous lecture I mentioned, electrostatics has two fundamental laws, Coulomb's law and Gauss's law. Coulomb's law we already studied. So now let's focus on Gauss's law. Gauss's law constitutes one of the fundamental laws of electromagnetism. Gauss's law states that the total electric flux represented by psi through any closed surface is equal to the total charge enclosed by that surface. That means the total electric flux psi is equal to the total charge enclosed by that surface represented by Q enclosed. So we know psi is equal to the total flux, right? Psi is the total electric flux, that is surface integral d psi. That is equal to, electric flux is also related to electric flux density as d dot integral d dot ds. And as per our Gauss's law, electric flux is equal to total charge enclosed. And that's equal to integral rho v dv. And Q, just from this equation itself, I can write the total charge enclosed Q is equal to surface integral d dot ds, and that is equal to volume integral rho v dv. To this particular equation, let's apply divergence theorem. So by applying divergence theorem, this middle term, surface integral d dot ds is equal to, that can be converted to volume integral as volume integral del dot d dv. So here I have applied divergence theorem. So now let's compare these two equations. Okay, let's say this is equation number 2 and this is equation number 3. Compare these two equations. Okay, this is volume integral, this term is volume integral, and here also we have a volume integral term. So we can compare the volume integral terms, and what you will get when you compare these two terms, what did you see there? That is rho v is equal to del dot d. So rho v is equal to del dot d, and this is our first Maxwell's equation. Rho v is equal to del dot d. This is the first of the 4 Maxwell's equations. And this equation states that the volume charge density, that is the rho v, is same as the divergence of electric flux density. Del dot d represents the divergence of electric flux density. So this Maxwell's equation, we can write it in integral form and we can also represent it in differential form. So in integral form, it is surface integral d dot ds equal to volume integral rho v dv. Or in differential form or in point form, we can represent rho v is equal to del dot d. So Gauss's law, it is an alternate statement of Coulomb's law. So proper application of the divergence theorem to Coulomb's law, that will result in Gauss's law. And Gauss's law provides an easy means of finding electric field intensity or electric flux density for symmetrical charge distributions such as point charge, infinite line charge, infinite cylindrical surface, or even a spherical distribution of charge. Whether the charge distribution is symmetric or not, Gauss's law always holds. Means, what does the Gauss's law state? It states the total electric flux through any closed surface is equal to the total charge enclosed by that surface. That will always hold whether the charge distribution is symmetric or not. But Gauss's law cannot be used to determine the electric field intensity or electric flux density when the charge distribution is not symmetric. Okay, that means it is easy to use Gauss's law to determine the electric field intensity or electric flux density when the charge distribution is symmetric. If the charge distribution is not symmetric, then we don't prefer Gauss's law. We can go with Coulomb's law. Now let's look on to one example for the better understanding of Gauss's law. Consider the charge distribution as shown in this figure, where V1 and V2 are the closed surfaces or volumes. The total flux leaving V1 is 10 minus 5. That's equal to 5 nanocoulomb. 10 nanocoulomb minus 5 nanocoulomb. That is equal to 5 nanocoulombs. Because only 10 nanocoulomb and minus 5 nanocoulomb are enclosed by V1. Though charges 20 nanocoulomb and 50 nanocoulomb, though they are present but they are outside. So 20 nanocoulomb and 50 nanocoulomb, they don't contribute to the flux crossing V1. So the net flux crossing V1 according to Gauss's law is equal to 5 nanocoulombs. Similarly, the total flux leaving the volume V2 is 0. Why it is 0? Because this volume, it encloses no charge. V2 encloses no charge. Applications of Gauss's law. The procedure for applying Gauss's law to calculate the electric field involves: first, we have to check whether symmetry exists. Because I mentioned already, Gauss's law is easier if there is a symmetric charge distribution. So that is the first step we have to check. We have to know whether symmetry exists. Once symmetric charge distribution exists, we need to construct a mathematical closed surface, or that is also called Gaussian surface. Second, the surface is chosen such that the electric flux density D is normal or tangential to the Gaussian surface. Right? When D is normal to the surface, we have D dot ds is equal to d ds, and when D is tangential to the surface, we have d dot ds is equal to 0. So thus we must choose a surface that has some of the symmetry exhibited by the charge distribution. So the ideas of Gauss's law can now be applied to special cases such as point charge, infinite line charge, infinite sheet of charge, and uniformly charged sphere. So now we will look on to apply Gauss's law into each of these cases. Applying Gauss's law to a point charge. Consider a point charge Q located at the origin. To determine the electric flux density at a point P, choose a spherical surface containing P satisfying the symmetry. So here a spherical surface centered at the origin is the Gaussian surface, and D is normal to the Gaussian surface. D is electric flux density, so that is equal to dr AR. From Gauss's law, we know total electric flux is equal to total charge enclosed, and we have already seen Q is equal to total charge is equal to surface integral d dot ds. So here we have our electric flux density D is equal to dr AR. So we have dr surface integral ds, and that's equal to dr 4 pi r square. The surface integral ds, this is the surface area of the Gaussian surface. Here we have a spherical Gaussian surface. So the area of a sphere, that is 4 pi r square. So it's very clear, Q is equal to dr 4 pi r square. So from this equation, we get electric flux density D is equal to Q by 4 pi r square AR. So we have applied Gauss's law in the case of a point charge to determine the electric flux density. So if you know electric flux density, how will you compute electric field intensity? E is equal to D by epsilon 0. That is, this answer divided by epsilon 0 will give you the electric field intensity. Second case, Gauss's law applied to infinite line charge. Consider an infinite line of uniform charge Royal Coulomb per meter that lies along the z-axis, this one. To determine the electric flux density at a point P, choose a cylindrical surface containing P to satisfy the symmetry condition. So this is our Gaussian surface. The cylindrical surface is the Gaussian surface. Here the electric flux density, it is constant and it is normal to the cylindrical Gaussian surface. So we can write D is equal to D rho A rho. It is along rho, where rho is the radius of the cylinder. Applying Gauss's law to an arbitrary length L of the line, we get the total charge enclosed Q is equal to rho L into L. That is equal to integral D dot ds, that is equal to D rho ds, and that's equal to D rho 2 pi rho L. So here we have to note one point. The integral D dot ds evaluated on the top and bottom surface of the cylinder. The top and bottom surface of the cylinder is 0. Why it is 0? Because the electric flux density is tangential to those surfaces. That is why we get this closed integral ds as 2 pi rho L. So from this equation, we can compute electric flux density D is equal to rho L divided by 2 pi rho A rho, where this rho suffix L, that is the line charge density. So once you have electric flux density D, how will you compute electric field intensity? D is equal to E is equal to D by epsilon 0. So this answer divided by epsilon 0 will give you the electric field intensity. Gauss's law applied to an infinite sheet of charge. Consider the infinite sheet of charge rho s Coulomb per meter square, an infinite sheet of charge with rho s Coulomb per meter square lying along z equal to 0 plane. To determine the electric flux density at a point P, so here is our infinite sheet of charge. To determine the electric flux density at a point P, we choose a rectangular box. That is cut symmetrically by the sheet of charge and has two of its faces parallel to the sheet as shown here. So here the electric flux density D is normal to the sheet. It is normal to the sheet. So we can write D is equal to dz az. Now let's apply Gauss's law. By applying Gauss's law, we get the total charge enclosed, that is rho s integral ds, is equal to closed integral d dot ds, that is equal to dz into integral, we have a top face and we have the bottom face. So it is integral over the top face ds plus integrating over the bottom face ds. The d dot ds evaluated on the sides, that is evaluated on the sides of the rectangular box, are 0. Why? Because there are no components for d along the x-axis and along the y-axis. So if each face has an area A, then we have rho s into A is equal to dz into A plus A. dz into A plus A. So from this we will get D, the electric flux density, is equal to rho s by 2 Az. So if you get electric flux density, how will you find the electric field intensity? That is equal to D by epsilon 0. So that is equal to rho s by 2 epsilon 0 Az. So now we have applied Gauss's law to a point charge, to an infinite line charge and to infinite sheet of charge. So I'm giving you one homework. Try applying Gauss's law to a uniformly charged sphere. Okay, so just try it. Let's work out one problem now. Given that the electric flux density D is equal to Z rho cos square phi Az coulomb per meter square. Calculate the charge density at 1, pi by 3, 3. This is the point. And the total charge enclosed by the cylinder of radius 1 meter with -2 less than or equal to z less than 2 meters. So we are asked to find the charge enclosed by the cylinder. So let's start. What we have is, we have to calculate the charge density also. That also we have to calculate. So we need an equation that relates our electric flux density with the charge density. Yes, I hope you will be recollecting the equation. Rho v is equal to del dot d. And we have the electric flux density given in our question. So first you have to compute del dot d. Okay. So here the electric flux density, it has got only a z component. So del dot d is equal to dou dz by dou z, that is equal to rho cos square phi. Calculate the charge density at the point 1 pi by 4 3. So at 1 pi by 4 3, rho v is equal to, where rho is equal to 1, phi is equal to pi by 4, we'll get rho is equal to 1 into cos square pi by 4, and that is equal to 0.5 coulomb per meter cube. So we are done with the first part. We calculated the charge density. What's the second part? Calculate the total charge enclosed by the cylinder. So total charge enclosed by the cylinder Q, that is equal to integral volume integral rho v dv, that is equal to volume integral rho v. What is rho v? It is rho cos square phi, that is rho cos square phi, and dv. From cylindrical coordinate system basics, we know dv is equal to rho d phi d rho dz. So now let's apply the limits. The value of z is varying from -2 to 2. Z varying from -2 to 2. Phi varies from 0 to 2 pi. And rho is varying from 0 to 1. So we have integral z -2 to 2 dz. Integral over phi varying from 0 to 2 pi cos square phi d phi. Integral over rho varying from 0 to 1 rho square d rho. Just simplify it. You will get it like 4 pi into 1 by 3. So that means the total charge enclosed by the cylinder is equal to 4 pi by 3 coulombs. I have referred the textbook Elements of Electromagnetics, authored by Matthew Sadiku, as I suggest all my students to go through this textbook to get better understanding of the topics and about the subject. Thank you.